sinusoidal functions to model periodic phenomena not involving angles. So until now, we've always had our horizontal axis is angles from 0 to 360 we've been talking a lot about, and doing our stretch compressions, translations, shifts, all on that sort of axis. Now we're going to be applying the same to real life situations that do not involve angles. So the first one we have for ourselves here in example 1 is modeling alternating electrical current. So just to give you a quick basic understanding, really basic, of circuits, if you have a circuit, which is essentially just a path along which electricity travels, you could have a direct current, which would mean it's always going the same direction. Or you can have an alternating current, in which case the electricity doesn't travel around and around, it simply goes back and forth. It goes from here to here and here to here. So moving electrons is what generates the power for electricity. So they don't need to be going around and around and around. Alternating current just moves them back and forth. Okay, so yeah, that's basically the understanding here. So when we convert it into a sine wave, okay, you can have voltage and you can have energy where, say, the max output is this much, and then they're going to spin and go the other way that much, and then they're going to spin and go the other way at that voltage, okay? So it ends up creating a sine wave, this alternating current. So let's dig into example 1 and apply our knowledge. Example 1 on page 20 in your student book says, the electricity in most of the world is alternating current. Unlike the electricity from a battery, which always flows the same direction, AC electricity reverses direction in a cyclical fashion, back and forth, back and forth. The frequency of AC current in Canada is 60 hertz, meaning 60 complete cycles occur per second. So it switches direction 60 times each second. The maximum voltage is about 170 volts, and the voltage can be modeled using a sine function. So the first thing I'm going to do for us here is just get ourselves a sine function that is going to tell us about the voltage with respect to time, okay? So we have the same parameters. We've got A, V equals A times the sine, square bracket, K. Inside our bracket, instead of X, I'm going to use T. So we have T minus D, close off that bracket, plus C. All right, there's our parameters. There's our basic function for a sinusoidal function. Part A of example 1 asks, what is the period of a 60 hertz alternating current circuit? So we're told, well, if we're looking at the period length, we're looking at K, we're looking at horizontal stretch or compression, okay? So we're looking at this 60 complete cycles every second. So if you get every second, you get 60 complete cycles, okay? That's pretty tight. That means that we're going to have a period of 1/60th seconds, okay? So it's going to complete one full cycle in 1/60th of a second. Since there are 60 complete cycles per second, the period is 1/60th of a second. Okay? B, determine the value of K. Well, we're going to use the same strategy, okay? So we have period. The relationship here is between period length is 360 over K, all right? But we know that the period length is 1/60th. So now we have a proportion set up where we can calculate that K is basically going to be 60 times 360, Okay, I can write that algebraically. We can multiply both sides by k, and then multiply both sides by 1/60th, or sorry, divide both sides by 1/60th, or we can cross multiply. You get 1k equals 360 times 60. All right, so k is equal to 21,600. C, amplitude. We're told in the explanation that the maximum voltage is about 170 volts, and it's alternating. So if I just draw that out for you for a second, if we zoom in on a part of this, basically what we're saying is we're going to reach a max of 170, and down at the bottom end, they're going to get to negative 170, okay? So the amplitude is 170 volts. D, model the voltage with a suitably transformed sine function. Okay, so again, suitably transformed, we don't necessarily need to move this thing left or right. We're not told like when it gets plugged in or where it is at 0 seconds. But sine, right? Sine naturally goes through 0, 0 on its way up. Okay, so sine we won't have to transform any which direction. We just need to put in the parameters that we do have. All right, so we have our basic function v equals, and that's up here. For a, we have an amplitude of 170. Then we're going to have sine. We have a k of 21,600, but we haven't moved it left or right, so I can just write it like this, kt. Right, if I don't have the rest of this bracket, then I just have k and t, which is multiplication, so I can just write it like this without the brackets, and we haven't shifted it up or down. So this is an appropriate sinusoidal function using the information that we were given. Okay. E asks us to graph the function over 2 cycles using technology. Okay, so in order to graph only over 2 cycles, we actually don't need a very big frame. We can zoom right in on a little chunk of that horizontal axis because it's going to complete 1 cycle in 1/60th of a second. So it's going to complete 2 cycles in 1/30th of a second. And then our y-axis, we would want to zoom in so that we can get all the way up to like 200 and down to negative 200, okay? So we're zooming in so that we get like 1/60th of a second and 1/30th of a second, and our max and min should be 200 and negative 200. So go ahead and take a second to do that on Desmos so you can see what this looks like, and we'll meet back here. In example 2, we are asked to model the angle of the sun above the horizon on the summer solstice in Inuvik. If you know anything about the far north, on the summer solstice, they have the sun all day, 24 hours. The sun is visible, no sunset on that day. And so we're given the angle of the sun above the horizon. So at midnight, 12 o'clock, basically if you were here, right, and you were looking at the horizon, you would see the sun right here, okay, at an angle of 2.5 degrees or so. Okay, after midnight, it's still on its way down, so that angle would get even smaller. 1 a.m., 2 a.m., it's back there. 3 a.m., 4 a.m., 5 a.m., 6 a.m., it starts to look something like that. Okay, 7 a.m., 8 a.m., 10 a.m., 11 at noon, it's at 45 degrees. Okay, so you'd see the sun somewhere around here. And it's also, I mean, I only have a 2-dimensional picture, but it's moving across the sky, okay? So you'd be looking at the horizon, you know, this way, and then progressively across the sky, nice and low. You'd be looking at the sun as it traveled down again. Anyway, that's what's happening. So you have a table of values in front of you that relates the time of day after midnight to the angle at which you would see the sun in relationship to the horizon. So we are going to use the table to determine a sinusoidal model for the angle of the sun above the horizon. Okay, so again, we're going to get the parameters a and k, but then we're also going to notice that in the case of a sine function, it's not going to go through like that, because we notice that it's actually reaching its minimum at 1 hour past midnight, okay? And it's all positive values. So we're going to be somewhere, like if I had 1, 2, all the way up to 24, okay? We're going to be reaching our minimum at 1 hour past midnight, which is 1.8. So it's going to be looking something, you know, I don't know, something like that. Yeah, if we get a view for this, the sun is going up to its max and then back down, and then you're done. Okay? So let's go ahead and find out some of our parameters. I've got the general function up here, and from the table we can see that the maximum angle, so here's a really good way if you're from a table of values, from actual data, and you need to generate these parameters, you need the max and the min and all of those sorts of things, okay? So maximum, it hits it at 46 degrees. That's in the 13th hour, 46 degrees. And we'll also check where our minimum is. The minimum angle is at the first hour, which is 1.8 degrees. And from those two pieces of information, okay, we can calculate the amplitude, which is max minus min over 2, right? Halfway between the max and the min. So we've got 46 minus 8 divided by 2, which is 44.2 divided by 2, which is 22.1. Okay, so this is A, amplitude. Here, just go A equals 22.1. What else do we have here? We can talk about the vertical shift. Okay, so we're going to find our new rest, which is going to give us the value of C over here. What is that? Well, our vertical shift, or well, we'll call it vertical shift. Vert shift is finding the average of the max and the min. So that's taking the max plus the min divided by 2, which is 46 plus 1.8 over 2, which is 47.8 divided by 2, which is 23.9. So this is our new rest. We have a rest here, which is also going to be the value of C. Okay? Now, the sine wave starts, that means, at the rest, right? So let me just sketch it out. Sine wave, this is 0. We've moved our rest up to here, which means our sine wave would typically look like that, okay? But we notice that we need to have a shift here because we are not going to hit our rest at time 0. We actually hit our rest at, when do we hit it? Check out that chart. So if our rest is 23.9 or 24, then we hit it right between the 7th and 8th hour. So we actually need this thing to come up from the rest right about there. So we actually need to move this 7.5 hours to the right, okay? So we actually have a D of 7.5, okay? And let's write a little note. If you want to draw this picture, you can to explain it. And I'll just write a little note alongside it. In this case, that is after applying our vertical shift, okay? The sine wave starts at 23.9. That's what the sine wave does, right? It starts, it goes through 0, 0, which in this case is not 0, 0, it's 0, 23.9, but it goes through 0 and the rest. The sine wave starts at 23.9, so where does 23.9 occur in our data? This is at 7.5 hours past midnight. Okay, therefore D is approximately 7.5. Okay, so we have A, we have C, we have D. Now we're just looking for K, which relates to period length. The period length in this situation, well, it's 1 day. So the period length is 24 hours. Okay, period length 24 hours. And that will help us to determine K, because period length is equal to 360 over K. And so we do our algebra on this. You could even think of this as like a little division multiplication triangle here where you have 360, K, and 24. So K is 360 divided by 24. So K is 15. And from all of this information, we have our 4 parameters. We can simply plug those into our general function. And I'll fit it right down here in this little space. So we have, and it's not volume and time anymore, it's the angle above the horizon. So it's h of t. So here we have h of t is equal to a, which we determined was 22.1, times the sine of, and we have all our parameters, so I'm going to be using the square brackets, a k of 15 times t minus d, and d is here, 7.5, close it off, plus c, 23.9. All right, and there you have a function that models the situation with the sun above the horizon on the summer solstice in Inuvik. The last thing we need to do here, C says, B says graph it. Graph the points on the table on the same set of axes as your model to verify the fit. So in Desmos, you would create a table, you would input all of those pieces of data, and then you would also graph the function that we described here. And then we would describe how good of a fit it is, okay? It's a pretty good fit. It's not perfect. Also, the real period length is not exactly 24 hours, which is part of why you don't get such a perfect fit. And the Earth's movement around the sun can also accommodate for a little bit of variation there as it spins, right? In example 3, we're able to model a predator-prey population relationship. If you know anything about predator-prey relationships with regard to population, if it's a pretty isolated setting, then these populations will depend heavily upon each other. So let's just hypothetically take deer and wolf, okay? Deer and wolf. Now, if you're the prey, which is the deer, if you know anything about trophic levels and the food chain, then there are more deer than wolves. Okay, as you move up the food chain, there are fewer of those animals per capita. Okay, so the prey has a greater population to begin with. So let's just start that wave. Okay, let's say the prey population of the prey is on the rise. Okay, then what happens is the predator, their curve will follow this curve. So as the prey is on the rise, the predators will start to be on the rise. But now look, as the predator's population is on the rise, they start eating a lot of prey, and the prey population starts to dip. Okay, I drew this a little high. I'll draw it a bit lower. Now, as the prey population begins to dip, what happens? Well, the predator population starts to dip. There's not as much food to sustain them. And as the predator population is dipping, that gives the prey an opportunity to reproduce safely, and their population starts to grow. Well, after their population starts to grow, what happens? Sure enough, the predators have more food to sustain more pups, and their population starts to grow. And so you can see how these they just follow each other, right? As the prey goes up, then the predator slightly behind starts to go up. The prey will reach its max. As the predators are rising, then they'll start to decline. As soon as they reach kind of a certain point where there's not enough food for the predators, they start to decline. As they decline, the prey are able to produce more. So these are really involved, interdependent population graphs. Sinusoidal functions, up and down, they depend on each other. Okay, so that's what we're looking at in example 3. Here we go. Predator-prey relationships can be modeled using sinusoidal functions. Prey in a given area can be modeled by the function n of t, so the number of animals with respect to time, is equal to 250 times the sine of 90t plus 500. All right, here we go, where t is the number of years since 1990, okay? T is the number of years since 1990. So in A, what is the population of the prey in 1990? So what it's asking is, what is happening when t is 0? Well, if you think to your knowledge of the unit circle or the basic sinusoidal function, where if t is 0 and we have the sine of 0, okay, then no time has passed. Well, we're right here because there's no phase shift in this equation. So this whole portion of that equation becomes 0, right? Because the 0 times 90 is 0. The sine of 0 is 0. And 250 times 0 is 0. So all we're left here, if t is 0, is positive 500. All right? So if we're thinking about that, then in A, we can record, we're going to sub t equals 0. And population in 1990 was 500. B, when did the population reach its maximum? So for this one, you could just go to Desmos. You could punch in this calculation, this formula, and you could find the maximum, okay? And you would find that it occurred. You could do it algebraically too, okay? We could, you know, apply our k value, our compression, and we would get this as well. But we're going to just do it on Desmos and draw it out, and we've determined that the maximum first occurs after 1 year. So in 1991, I'll say after 1 year, comma, in 1991. C, what was the maximum population at this time? Well, really, you can just take this function and put 1 in for t, okay? And that's pretty easy for us to do in our heads because we know 90 times 1 is 90. We know that the sine of 90 is where the graph sine of x will reach its maximum, sine of 90, which a maximum of 1. The sine of 90 is 1. You can put that in your calculator. 1 times 250 is 250, plus 500 is 750. So population in 1991 was 750, a good year for the prey. D, when did the population reach its minimum? Again, we're just going to use your Desmos graph, and you can scan it until you find the minimum. It occurred at the end of 3 years. So after 3 years in 1993. And what was the population there? Well, if you get the minimum, then you would have a sign value of -1. -1 times 250 is -250. Plus 500 would be +250, okay? So population 1993 is 250. That's where it's going to be its minimum. And we can kind of see what's happening already, okay? This tells you that you have a rest at 500, and this tells you that it's going to go up to 250 above that and down to 250 below that. So obviously this one is 750 and this one is 250, and the population of prey stays somewhere in that range, okay, from year to year, approximately. F, how many years passed between maximum populations? So how many years passed from here to here, which is essentially just asking what's the period length here. We could get that from our equation, or you can use your graph that you have there. The next maximum, EDF, next max occurs in 1995. So 4 years passes between them. Okay, so sinusoidal functions can be used to model periodic phenomena, even if it doesn't involve angles. Amplitude, phase shift, period, vertical shift of the basic sine or cosine function can be adjusted to fit any periodic situation, any recurring pattern, okay? You can use technology, Desmos, to just quickly graph these things and learn a lot about the situation. And yeah, you can solve problems using that graph as well. Your practice problems for lesson 5.6 are found on page 337, numbers 1 through 11. Enjoy.